Good morning everyone. Today continuation of aseptic equipment design class. Today we are going to see aseptic process design. So and we also will do few problems to understand the product characteristics and how it affects the equipment design. And as I mentioned you in the last lecture itself, these three lectures are interrelated to each other. So, without knowing process design you cannot design a equipment, and equipment design needs process parameters. So, all are interlinked, and when you are going through the lectures, so please try to connect these three lectures very carefully, because some of the information I would take it from the previous lecture, and from here some of the informations you would require for the previous lecture of aseptic equipment design. So, when you read about all three lectures together, as I mentioned earlier. It is unlike previous lectures. Previous lectures are on specific topic, but these three lectures are on same topic, which should require information from all three lectures for a better understanding. Right. So, we will start with thermal process calculation. So, this we have discussed already, D, Z and F value. So, I am going to tell here only the critical points. I am not going to discuss how to calculate D value or Z value or F value once again. So, the process given to a food material is quantified in terms of multiples of D value at a reference temperature. So, whether it is a 6D process or 12D process. So, we already have seen in many of the lectures 121 is nothing but around 0.23 minute. So, based on that 6D process, which requires for the pasteurization, which is a mild treatment applicable for acid food, and sometimes I follow 12D process, which is nothing but a sterilization, which is nothing but for the sterilization process. So, which is also referred as a F value at a reference condition, right, which is nothing but a F naught. So, the accepted reference temperature for sterilization is 121 and that of the pasteurization is 83 around. So, here are the examples given. If it is ultra pasteurization, the storage should be of refrigerated storage. So, the heat and hold is 138 for 2 seconds. The equivalent F value is nothing but 1.5 minute. And this A is why it is given, it is a minimum value. So, your safe process requires more than this value, and minimum to destroy Clostridium botulinum spores non-refrigerated. So, 138 degree for 4 seconds, the equivalent F naught is 3 minute, and commercial sterility non-refrigerated 138 degree centigrade for about 8 seconds, the equivalent F naught is 6 minute. And European UHT, so I might have referred in the previous lectures as a UK standard and US standard. So, this is 135 degree for 3 seconds and 140 for 3 seconds. So, I already told in UK standards most of the time they also take care the nutrient value. So, based on which instead of going for high temperature and long time process, they go for low temperature and hold it for particular time. Right, the equivalent F naught is 1.22 and 3.87 minute. And lower D and Z values for vegetative cells imply that they can be destroyed faster than spores, right. So, you have a vegetative cells and as well as the spores mostly be removed in the sterilization process. Vegetative cells pasteurization temperature is high enough. So, pasteurization, the D and Z values are low. So, that means they are destroyed faster compared to spores. Enzyme destruction takes more time than the destruction of microorganism, because if the two are done at same temperature at same time, then we will not be able to maintain certain enzymes which are essential for the food quality. And quality factors and nutrients are relatively stable under high temperature short term thermal process, HT, ST, that is what we most of the time follow, this HT, ST. And the target for sterilizing value or F naught is set based on the product type and its intended use. So, intended use is whether it is a refrigerated storage or normal ambient conditions. So, based on that my F naught value vary, and also product type, whether it is a liquid or liquid with particulate. So, based on that also F naught value, because this liquid is nothing but a convection only, but liquid with particulates. So, I need to take a conduction convection. So, just we have in few more lectures back we have also discussed heat penetration testing, these concepts. And the target for setting up of thermal process could be based on microbial kinetics or enzyme, right. Sometimes my interest would be of deactivation of enzyme. So, that is done at the pasteurization. So, that also one of the target for setting up the thermal process. In case of fruit juices and several high acid beverages, the target is in enzyme inactivation only, just I told pasteurization. So, these are all high acid beverages. So, there my main aim is enzyme inactivation only instead of microbial kill. So, there I use the 6D log only, not for 12D log reduction. And flow characteristics of the product also affects the thermal process design. So, what are all they? Fluid viscosity, density and velocity. For the previous lecture we have seen in the equipment design. So, based on RE only I can fix the velocity of the product, which was nothing but U max. So, to calculate Reynolds number, so I would require all these information: velocity, density as well as fluid viscosity, size and shape of the pipe. So, here also D comes, D rho U upon mu. And surface roughness of the equipment also matters, because the roughness increases the heat transfer, and also it goes to turbulent because of roughness in the equipment surface. So, this is RE definition. So, this we have used in the last lecture itself to do the problem. And this is the normal laminar velocity profile, because your steam lines are parallel. So, it's like a sheet like kind of like flow. So, this is the U equal to 0. At the wall there is no slip boundary condition, that layer will not move, and you will get the parabolic velocity profile. Right. And for the turbulent region, then you will get mixing of streamlines. So, these kind of profile, and you will get more flatter profile. Also remember, if there is cooling and heating, so this is maintained at isothermal condition, you would get this kind of profile. But if it is a heated or cold wall, then heated wall make the flow profile flatter by causing more wall slippage. Wall slippage would be more, so that you will get more flatter profile. If it is a cooling, then the much faster center velocity than the isothermal condition. Faster center velocity in the sense, center element is nothing but U max. So, this will be much faster than the rest of the particles. And in the flow characteristics, this we have done in the last class problem itself. So, the Reynolds number is 2300. I told there may be 2100 to 300. So, different books follow different numbers, and definitely greater than 4000, it is a turbulent region. So, in between it is a transition. So, this T minimum is nothing but a residence time, how much time the particle spends inside the tube. So, this is nothing but L is length of the tube, V max is nothing but maximum velocity. So, if it is a laminar, so your V max is 2 into V average, and if it is a turbulent, then it is 1.22 times faster than the average velocity. Then your V max is nothing but 1.22 into V average. Right. And one more property what we have seen is the viscosity, right. The viscosity and shear stress relation is nothing but tau is equal to mu into dV upon dy. So, this we call it as a shear rate from the velocity profile, and this is nothing but a viscosity, and this is nothing but shear stress. Right. So, this we call it as a Newton law of viscosity, Newtonian law of viscosity. Right, the fluids which follow this particular law, which is nothing but tau is proportional to shear stress is proportional to shear rate. So, those fluids are called Newtonian fluids, but most of the food products are non-Newtonian fluids. So, they follow this formula, which is nothing but tau equal to k gamma, this is nothing but a shear rate. So, power n. So, this power n comes from the power law model, or otherwise it is called as flow behavior index, and k is nothing but a flow consistency index. If the value of n is less than 1, then the fluid has a pseudoplastic or shear rate thinning behavior. If n is equal to 1, it is Newtonian. So, here I told, and if it is n is more than 1, then it is a dilatant. The values of k and n are temperature dependent, right. So, when you increase the temperature for the liquids, the viscosity decreases, right. When you increase the temperature, as per the kinetic theory of gases, then for liquid it decreases, for gases it will increases. And here we use the most of the food products in either in liquids or liquid with particulate solid form. So, obviously when you increase the temperature, the viscosity should decrease, but it is not true for all the food materials, because there may be a coagulation or there may be a gelation. So, in that case, even if you increase the temperature, your viscosity would increase. So, that is the reason we need to study the rheological behavior of the products, food products, by experimental data. And here we told k and n are function of temperature, and mostly k is very much sensitive to the temperature. It is very important to have experimental data on rheological behavior of the products to be processed aseptically, because of this reason. It is always not true, when you increase the temperature your viscosity would get decrease. There may be a gelation or coagulation property or glass transition temperature, because of which even if you increase the temperature, there may be an increase in viscosity. And the next important characteristics is residence time distribution. This is the how much time my fluid particle spends inside the tube. Why it is important here in the sense, so in previous thermal processing we have not discussed, right, but here it is a pumpable fluid, it is in the continuous flow, and also it is a liquid food products or liquid with particulates. So, here as per the FDA or CFR or the GMP, it says that, so the each point, for example, if you are pasteurizing the milk, each food particle of the milk should be at the pasteurization temperature or sterilization temperature, right. So, it is very much important to know each and every particle spends the required time and required temperature. So, because of which the pumpable fluids, the RTD calculations are very much important to get to know either there is a change in the residence time distribution of the particles or not, right. So, the experimental determination of residence time distribution is carried out by measuring the response of the inert tracer injected into the product stream, so called stimulus response technique. So, how do I understand? I cannot directly do anything in the product. So, I will introduce the tracer system and trace the tracer system and get to know how much time it spends inside the tube or inside the heating tube. So, this system is called stimulus response. The traces are usually soluble dye, salt or acid that can be detected at the exit of the test zone. The detection of changes at the output stream of a test zone based on known changes in the input stream, right. So, either it may be of step input or pulse input or sinusoidal input. So, for the known input, what should be my output stream response, right. In the step input, in which the input concentration of a tracer or other measurable component is changed from one steady level to another. So, for example, this is my step input. So, immediately it rises to some other level, and pulse input, in which relatively small amount of tracer is injected into the feed stream at the shortest possible time. So, this is like this. So, this is pulse input, and sinusoidal is nothing but something of this kind. So, these two are very much easy to carry out experimental determination of RTD, but sinusoidal input is a bit difficult to carry out. Here the variation is changed and thus generating the frequency response diagram is needed to analyze the output characteristics of the tracer particle. The quantification of RTD provides information on minimum and maximum time spent by the fluid element in the system. So, this we have seen, for example, so this is my pipe, so my particle comes, right. So, this is, we call it as a plug flow. So, that means, so each and every particle spends same time because the velocity is plug profile. So, each and every particle, for example, I considered 3 particles. So, this spends same time and it exits. So, it also provides insight into channeling or dead space. So, for example, if I am not finding the second particle or it comes a bit late, right. So, at t equal to 1 second I am finding 1 and 3, then after 2 seconds then this comes. So, that means there may be a delay due to some of the false diagnostics. It shows me false diagnostics, something is happening inside the system, and also if there is any channeling or dead space, then there will not be any flow at this point. For example, it is a dead space, then there will not be any flow. So, this also can be diagnosed using RTD studies. Experimental determination of RTD is required by the US FDA during the commissioning trials itself. So, while commissioning trial, we is supposed to submit the experimental determination of RTD. In laminar flow, using coiled tubes instead of straight tubes has been suggested as a means to achieve radial mixing of the fluids due to Dean's effect, which occurs as a result of imbalanced centrifugal force of the flow in the curved tube. So, in laminar flow, which is nothing but a thin sheets, your product is flowing in the streamlined way without mixing between the streamlines. So, here what is suggested is to have a coiled tubes. So, what is Dean effect is? Dean effect is nothing but, for example, if I have a concentrate tube, so then my we have just seen, right. So, my profile would be of this shape. So, I am not doing it correctly. So, this is nothing but parabolic shape velocity profile you would get, right. But what Dean's effect says is, so if you have a coiled tubes, then there will be a secondary vertices, right. So, that means, so your flow will be of this kind, right. So, this increases the mixing, right. If you remember, I already told in the I think previous lecture, there is a reason for static mixture to be used. There it was used to increase the mixing in the continuous flow line, but if you take care of, instead of straight tubes, coiled tubes, this secondary flow itself will take care of the mixing part, because it generates the secondary vertices instead of normal what we see in normal tube, right. Normal straight tube you will get parabolic velocity profile only, right. So, this is what discussed here. In laminar flow, using coiled tubes instead of straight tubes has been suggested as a means to achieve radial mixing of the fluids due to Dean's effect. This is nothing but a Dean's effect, which occurs as a result of imbalanced centrifugal force of the flow in the curved tube. So, it is mainly due to centripetal force, right. And the secondary flow pattern can be described as a double vertex circulation in the perpendicular plane to the main flow. This is the main flow, this is a perpendicular plane, and superimposed on the velocity profile in the axial direction. And the existence of Dean effect helps enhance the heat transfer and tube flow as well. So, as we have seen, so definitely it increases the mixing. If you increase the mixing, obviously the heat transfer is enhanced. So, here are we are going to do some of the example problems, how to design a lethality of the process. I think these two examples are done in last two lecture itself. So, this is nothing but a calculating the 12D process, I guess. So, the D value is nothing but log of 10 to the power of 12 spores into 10 to the power of 0. So, which comes around 12, and I have a D value, reference D value given, which is nothing but 0.37 minute. So, this is a D value into, so this is nothing but 12 into 0.37. So, this is coming around 4.4 minute, and this is nothing but pectin esterase enzyme in orange juice pulp is a heat resistant enzyme and is inactivated in the aseptic processing of orange juice with pulp. Its D and Z values are available from the literature. At 90 degree D90 is given, which is in minutes as well as in seconds, and Z is also given. So, we supposed to calculate at 100. So, yesterday one of the problem we have used the formula which is nothing but log D upon D naught, which is equivalent to T minus T naught upon Z. So, which gives me D equal to D naught 10 to the power of T minus, sorry, this is T naught minus T upon Z. So, T naught minus T upon Z. So, I supposed to calculate it 90. So, D naught 10 to the power of T naught minus 90 upon Z. So, then D at 100 is nothing but D naught 10 to the power of T naught minus 100 upon Z. So, what I wanted is I wanted it 100. So, that is nothing but D90. So, this will go and same reference value will go. So, this is nothing but 10 to the power of D100 upon D90 is nothing but 90 minus 100 divided by 6.5, because here Z value is given. So, D90 value is nothing but 0.53 seconds or 31.8 second into this 10 to the power of 90 minus 100 upon 6.5 is nothing but 0.03. So, I will get D at 100 is around 0.92 seconds. I have used in seconds. So, you will get. So, remember here your Z value is given as a 6.5. So, for example, if I calculate D at 96.5, so how it will become 31.8 seconds and 10 to the power of 90 minus 96.5 upon 6.5. So, it would give me 3.18 seconds. So, this is what the definition goes. So, to kill the 1 log, right. So, here I got 31.8 seconds. So, here I got 31.8 second. So, 1 Z value give me 1 log reduction in the D value, just to make you understand that concept. Okay, so, here are the main problem. The fluid milk processing plant is designed to sterilize the milk for aseptic processing. The various unit operations involved and the temperature profile is shown. I am sorry for this particular slide, but I wanted to show you all three in one particular slide itself. Shown using the thermal processing calculations, calculate the total lethality, which is nothing but a F naught value. For this process, for simplicity, use the following assumption. One is uniform product temperature in each section, as well as the logarithmic bacteria kill over the process temperature, right. We supposed to assume, and the sections are given: preheater, homogenizer, regenerative heating, holding, and steam heater, and holding tube, and regenerative cooling. So, this is the diagram. So, 0 to 1, which is nothing but a preheater, the temperature is varying from 50 to 71, and the second is not specified, or I might have forgot to mention. And here then the next one is homogenizer, or 1 to 2. 1 to 2 is nothing but 71 to 74, it is time is 2.5 seconds, and 2 to 3, which was nothing but a regenerative heating here. So, here it is heated 74 to 95 degree centigrade, about 4.5 second, and the 3 to 4 is holding. So, it is a constant temperature which is nothing but 95 degree centigrade about 2 seconds. Then steam heater it goes to, so there 95 to 139 and it spends 17.5 seconds. Remember the temperature versus T relation is given because it is not a one go 95 to 39. So, it follows this time and temperature follows this particular equation which is nothing but T equal to 142.3 into 1 minus 0.3324 e power minus 0.1524 T. And holding tube again 139 degree, right. So, which spends 2.4 seconds, then it is a cooling section 130 to 50 and the spending time is 21.6 second and T is nothing but 139 minus 4.12 T. It follows the time and temperature relation. So, to decrease the temperature from 139 to 50 degree for about 21.6 second. So, we are going to do the problem. The first one is I need to see what is my total lethality. The total lethality happens, one is in lethality rate which happens in the heat exchanger section. So, which is nothing but a heating section. Then what is happening at the holding tube HT and the same lethality rate happens at cooling section. So, I will just to put HT because HE is nothing but heat exchanger. So, here remember here it is a constant temperature process. So, cooling and heating has T as a function of T, right. If you remember the lethality rate formula is nothing but 10 to the power of T minus T reference upon Z. So, remember this is for if it is a constant temperature process and if it is a if I supposed to calculate here in the heating section, then I supposed to be calculating 0 to T and 10 to the power of T of T minus T reference divided by Z into dt, right. So, this is nothing but LR, right. So, if it is a constant temperature process, it is nothing but LR into del T if it is a constant temperature process, right. So, based on which we are going to calculate first in the heating section HT. So, if you remember the temperature relation is given which is nothing but T equal to 142.3 into 1 minus 0.3324 e power minus 0.1524 into T. So, based on which we are going to calculate time versus temperature. So, temperature in degree centigrade, time in seconds. So, I am taking 0, 2.92 and 5.84, 8.76, 11.68, 14.6 and 17.5. So, using this formula, so we are going to calculate the temperatures which is nothing but 95. So, how did I obtain this 95? So, I will substitute in the T formula which is nothing but 142.3 into 1 minus 0.3324 e power minus 0.1524 into T here is the time is 0, alright. So, from this I will get 95. So, for 2.92 I will substitute 2.92, then I will get what is the required temperature here, and 5.84 I will substitute here and what is the correct temperature here. So, if you do the calculations, then you would be getting 123, 130, 134, 137 and then 139. So, I got time versus temperature relation using the equation given for the HT section. So, then I supposed to calculate LR. So, LR I have a formula which is nothing but So, we are not going to do integration here, I will tell you how to do that. So, we are just simply calculating 10 to the power of, so LR rate is here for example 0.0025 for this particular 0 and 95 time temperature combination. So, how did I calculate? So, it is nothing but 10 to the power of T, T is given 95, my reference temperature is 121 divided by my reference Z value is 10. So, I have assumed the assumption here is T equal to 121 and Z equal to 10, sorry T reference, right. So, from this I calculated the LR value. So, the T you will be substituting 95, 112, 123 or 130. So, then you calculate this particular column. So, which is nothing but 0.126 and 1.548, 7.762, 120, 21.5, 41.58, 63.31. So, before calculating the area under the curve, why I am supposed to calculate the area under the curve, I will come here. So, this is the LR versus time. So, this is nothing but a time x axis, right. So, what I have done here is I just plotted whatever I calculated here, the time versus LR. So, the curve looks like this. So, I will calculate what is the area under the curve. So, that is nothing but this particular value, which particular value here, right. So, here this I have calculated, this is LR into dt 0 to t, the total time is 17.5 and it starts from 0. So, if I calculate lethality rate in each time, so I will just draw a curve, then area under the curve, just you have to count the boxes. So, then you will directly get what is the time requirement for this particular lethality rate, or otherwise if you want to do numerically, then what you supposed to do I am telling. So, here what we supposed to calculate is LR at HT, so which is nothing but 0 to 17.5. So, LR we have already calculated, which is nothing but a T as a function of time minus T reference upon Z into dt, right. So, this I have already calculated because I have already calculated my time and temperature from the relation given, which is nothing but T as a f of t. Then I have now 0 to 17.5 LR, which is in y axis, and dt, which is dx, right. So, integral y dx I should be calculating, or numerically I can just calculate. So, yi dx I when I equal to 1 to n, right. So, I need one particular y value and dx is nothing but the difference between the time range. For example, here 0 to 5 seconds what is the y, and 5 to 10 second what is the y. So, for that what I supposed to do, if I want to calculate numerically, I need to take the average between these two, right, and take the dx as 2.92 minus 0. The first column I would be just putting 0 only. The second column how do I calculate is 0.0025 plus 0.126 upon 2. So, this would give me only one y, the x is nothing but 2.92 minus 0. So, which is coming around 0.19. So, the next value coming around 2.43, the next value is 13.46, the next value is 42.60, the next value is 92.10, then 152.01, right. The first value, which is nothing but for 0 time 95 degrees centigrade, LR of 0.025, I have just kept it 0 because I cannot calculate, because I supposed to have two values to make average, and dx value I need two value. to subtract two values to get the dx, right. So, I have kept first value as 0, the second value as 2.92 and 112 degree centigrade of the lethality rate of 0.126, it yields me 0.19, right. The third one, how do you calculate? 0.126 plus 1.548 divided by 2, which would give me one particular average y value into 5.84 minus 2.92. So, which would give me 2.43. So, like this you can calculate. Then finally, if you see here, it is a summation. So, if you sum it up, you are ending up getting 302.87 second, or which is approximately equal to 5 minutes. Right, you can do either this way, numerical calculation, which ends at 302.8 second. So, or you can do graphically as well. So, you draw a graph between time versus lethality rate and draw the curve and get the area under the curve directly. The second one is very much easy, because as I told earlier, LR at holding tube. So, which is nothing but a constant process, constant temperature process. So, LR into dt is nothing but LR into integral dt, which comes as LR into del t. So, LR is nothing but 10, the temperature is 139, the reference temperature is 121, the Z value is 10 into del t is nothing but 2.4 second, that is the holding time. So, you are getting 2.46 minute approximately. So, the next one what we supposed to calculate is LR in cooling section. So, the cooling section also, it is bit easy compared to heating section, but here also we have a temperature relation, but seemingly easy compared to heating section. So, how are we going to do? LR is nothing but 0 to 21.6 second, and this is a minimum maximum time limit, 10 to the power of, they have given time temperature relation, which is nothing but 139 minus 4.12 T minus reference temperature is 121, this is T time. So, this is 10 Z value into dt. So, this constant I will take it out, 10 to the power of 139 minus 121 upon 10. So, I have taken it out, 0 to 21.6 into 10 to the power of 4.12 upon 10. So, which is nothing but minus 4.12 T, right. So, this is 61.25, then when you integrate it, it is nothing but minus 0.412 T upon minus 0.412, it has to be upper and lower limit to be substituted. So, if you calculate, then it comes around 150 seconds or around 2.5 minute. Right. So, now we have calculated lethality rate in all three sections, right. So, the total lethality rate is 5 minute plus 2.5 plus 2.5. So, I just rounded it off. So, totally it is coming around 10 minute, right. And remember your heating section as well as cooling section, it is around 7.5 minutes it spends in just heating and cooling, and 2.5 minute it is spending in holding tube. So, this is the way we are supposed to calculate any lethality rate of the process. And we will also see based on the product characteristics how to design a process, or how the product characteristics affect the process and product qualities. So, here it is given the processor uses the same equipment to process products flowing at a rate of 39 liter per minute with the different viscosities. The flow rate is same, but viscosity is different. How will the flow profile change with the changed viscosity of the product, and if processor changed the pipe diameter, how will the flow profile change? So, the flow profile means we have only one formula, d rho u upon mu. So, this is average velocity. So, what it is told is if I increase or decrease the viscosity, what happens, or if I increase or decrease the pipe diameter, what happens, right? How the flow profile changes. Flow profile in the sense, so either it is a laminar or turbulent or transition, right. So, how does it change? So, I am going to take it two examples. One is 2 centimeter pipe with 10 Cp. So, I am going to calculate what is my Reynolds number, and the same 10 Cp viscosity I will take, but it is a 5 centimeter pipe, and for the 5 centimeter dia pipe, then I will also use 2 Cp. Viscosity I will decrease, then I will observe what is the change in Reynolds number. The first one we are going to do Re, my diameter is 0.05 and my density I am just taking 1000 kg per meter cube, and the flow rate given is 39.4 liter per minute. So, I am going to change it by meter cube per minute, but what I need is average velocity. Average velocity is nothing but the volumetric flow rate 39.4 into 10 to the power of minus 3, 10 to the power of minus 3. So, which is converting liter into meter cube. Then you have your minute, I am converting into seconds. So, 1 minute is nothing but 60 seconds. So, what you get is 0.006 meter cube per second. So, I have converted just 39.4 liter per minute into meter cube per second. So, I got my, I am still keeping it as a volumetric flow rate only. So, when I calculate Reynolds number, then I will substitute volumetric flow rate as volumetric flow rate, because my diameter is changing. So, I am going to keep it the same like that only. So, here my Cp is 10 Cp. So, 10 into 10 to the power of minus 3. Cp is nothing but centipoise. So, which is nothing but 10 to the power of minus 3 kg per meter second. So, then I supposed to divide it by area to get velocity. Velocity is nothing but volumetric flow rate upon area, which is nothing but meter cube per second upon meter squared. So, which is meter per second. So, I supposed to calculate the area as well, 0.05 whole square into 4. So, the Reynolds number what I get is around 1528. So, 1528, which is in laminar region. The same way, if I calculate Reynolds number for 0.05 into 1000 into 0.006 into 4 divided by 2. 2 is in the sense I just changed the Cp from 10 Cp to 2 Cp, and into pi into 0.05 whole square. So, which is approximately 7643. So, which is turbulent, 7643, which is turbulent. The same way, if you calculate here by substituting 10 Cp and 2 centimeter, and you would be ending up around 3821. So, which might be of some transition. So, keeping diameter constant, if you decrease the viscosity, so your flow changes from laminar to turbulent. So, by keeping viscosity same and increment in the diameter 2 to 5 makes the flow from transition to laminar. So, this is the answer for this question. And this is about orange juice flows through a straight pipe. The internal diameter is given and length of the pipe is given. Flow rate of orange juice is given. What is the mean residence time of the orange juice in the pipe? So, we know mean residence time. So, in the last lecture itself we have seen, or this lecture also we have seen formulas. So, which is nothing but a volume upon volumetric flow rate. So, I supposed to calculate volume. So, volume is nothing but pi dl. So, pi is 3.14 and 5 centimeter dia is given 10 to the power of minus 2 into 6.5, so which is coming around 0.127 meter cube, and volumetric flow rate is already given 0.0127 divided by 0.01, so which comes around 1.27 minute. So, mean residence time is each particle spends 1.27 minute on an average. Okay. So, with that I would end this lecture, and also the I have just discussed here the mean residence time. So, when we were discussing the residence time distribution, we already told how to calculate the residence time distribution for each particle, and that is for each process, and that is a very much needed regulation when you go for the commercialization of the process. So, I would request you to follow maybe 11th spill of chemical reaction engineering to get to know about in depth about RTD studies for various input races. Okay. Otherwise, these are all references and additional resources which I used in this particular lecture, and all 3 lectures in fact. Thank you.